All right.
Okay, so welcome to today's Meow seminar. We're happy to have Oliver Korten here, who will tell us about the complexity of explicit constructions. Without further ado, please, Oliver.
Thank you, Jacob, and thank you very much for inviting me to talk here today. So yeah, I'm going to talk about some recent work trying to sort of and understand the complexity of explicit constructions, which I will explain what that is shortly. So sort of throughout math and computer science and combinatorics, like a really common tool that's used all over the place is the probabilistic. And I'll explain what that is if you don't know, but it's like a very common proof technique that's used to prove the existence of interesting and very useful objects. And so I'm going to throw up a bunch of examples that you don't have to know any specific one of them, but hopefully maybe you might have heard of one of them. There are all these sorts of like extremal combinatorial objects that come up a lot in theory of computing, where it's very easy to give this sort of non-constructive proof that these objects exist. But on the other hand, it's typically very hard to actually come up with explicit specific examples. So in graphs, for concentrators, these are less well known. Ramsey graphs, in the theory of Boolean functions and we have like sort of high complexity Boolean functions, randomness extractors, and in like matrices, you might have heard of like really strong error correcting code or rigid matrices. I'm just kind of throwing these out there. It's okay if you don't know what any of these specific examples are, but the point are that these are concrete combinatorial objects that arise in various computer science where, like I said, it's sort of an easy proof that they exist, but it's really hard to like match this proof with sort of a constructive way to come up with examples of these you can actually use in, for example, and so sort of it's been like a recurring situation problems that like there's this non-constructive, and over time sort of we need to develop a really rich mathematical theory to sort of match with constructive example. So just in case you have no idea what I'm talking about, you've never seen one of these proofs, I'm going to go through in my mind what sort of the simplest example is, and historically this is also the first example of the probabilistic method being used. So this are for these objects, Ramsey graphs. I'm going to describe it just as a type of Boolean matrix, but we can think of it as describing a bipartite graph if you want. So this is a matrix, just an n by n Boolean matrix, 0 and 1. I'm using like capital M to denote the matrix. And this is a n comma k Ramsey graph if the dimensions are n by n, and it has one property that if I look at any set of k rows and at least k columns, here I'm denoting that by A and B. If I look at the submatrix defined by rows and columns, then the matrix has to have at least one zero value rectangle and at least one value. So it can't have a large rectangle, which is all zeros or all ones. And, so these came up originally, were studied by Ramsey and by Erdos for some like purely combinatorial things, but later it became realized that these graphs are actually really cool for something called randomness extraction, which I won't get into in detail here, but the point is that they're not a mere curiosity; they're actually very useful in sort of the topic of derandomization. So, anyways, Erdos back in the 40s was looking at these, and he's the first proof of what we would now call the probabilistic, using what we would now call the probabilistic method, where he proved that these types of graphs exist, and even when we can take k to be as small as about log n. And I'll run the basic idea of the proof just because this is going to be sort of representative of a lot of the way these types of problems are proved. So the idea that he had was we're going to choose the matrix uniformly at random. So all of its entries are just independent 0, 1 random variables, and we're going to argue that in order to not be a Ramsey graph, to have some sort of unlike going to be almost the definition of being a Ramsey graph is if you fail to be a Ramsey graph, that means that you have a matrix which has this sort of very unlikely pattern of being completely one color. All zeros are all ones. And then you can argue that if I chose the matrix at random, I would have a very high probability of avoiding all of these kind of unlikely patterns. And so I would have, in particular, positive probability of like not Ramsey graph. In other words, being a Ramsey graph. So yeah, really quickly, the idea is we choose the matrix uniformly at random. If I look at some fixed columns, that defines a matrix which has k squared entries. Them has size k. And so for me, the entries at random, the probability I make all of those the same color, that's, you know, just exponential of k squared, because that's how many like coin flips were involved. So the probability like for a fixed AB is like exponential and negative k squared. And then probability that there exists a set of rows in column AB, would then I could just take a union bound. I can sum over all possible choices of A and B, and there's almost like n k squared of them, right? Because there's n k choices of A and n for B. So then I can say that this randomly chosen matrix does not see property is at most this expression I wrote, which is, you know, sum over all A and B. That's the n choose k squared, and then extremely small probability of coloring all of A cross B, which is exponential and minus k squared. And just work out those parameters. You can show that this is going to be, this probability is going to be much less than 1, provided I choose k to be suitably large. So yeah, this was a very influential Erdo-Schroeder. Is about like 3 pages long, and it gives this argument. And this sort of very creative idea here is we're trying to build this sort of weird mathematical object that it's not obvious when it exists. Argue it exists by arguing that it's essentially like like if I choose not completely at random, it would be very unlikely to exhibit a pattern which would sort of prevent it from having the property we want. Hope that made sense. Any questions? If this is confusing or I said something weird, please feel free to interrupt. So, so anyways, the crucial observation of this proof, which I've said again and again.
So there was one question in the chat that will we be assuming sort of that these objects, we're trying to construct objects that are abundant, or can we also construct sometimes rare objects, or the typical setting is that they're all over the place?
So I'll explain the question. I'll explain that soon. Basically, I'm going to be focusing on a certain class of objects which are to be abundant, and the classification we're going to be really specific to these, and it'll come why that is. But yeah, so we're sort of going to be focusing on objects which are in great abundance, and the sort of the probabilistic method proof like shows this by its nature. Yeah. So yeah, like I said, this type of proof, you know, the upside of it is that it's very simple, but it gives no sort of explicit example of, for in this case, a graph which has the Ramsey property. And in applications for this problem and for all these other problems, like sort of we really want not only that there exists a graph for an object that we want it to be efficiently produced by a deterministic algorithm. This is when like it would turn from becoming like sort of to being like something that's algorithmically useful to us. So like I said, there's like a host of these other problems. I have a few of them listed out on this page that have had like a very similar history where, you know, when people started considering them, they immediately tried this probabilistic proof. They found very easily that you can show these objects exist, but sort of over time, it's proven very difficult to match this with a constructive. And just a little key here, like, so for these selected problems I chose, some of them, the ones I marked in, there's been no progress. However, we essentially have an idea how to beat the non-constructive argument. The ones in purple, very significant progress, but there's still a significant between the non-constructive arguments. And then, like in the case, we've essentially solved this with years of hard work. And so the question that I'm trying to address here is, we establish sort of a unified complexity theory to address these explicit construction problems. Can we show ideally, would there be a universal way that we could just automatically turn a non-constructive proof into a constructive one? That would be very nice. Or at the very least, can we say that can we sort of describe some general problem which captures the complexity of making the probabilistic method constructive, and maybe show, like in the theory of NP completeness, that there's some sort of complete problems for this, so that if we could sort of, make a certain explicit construction problem explicit, that would sort of allow us to generalize that to problems. So, the analogy I'm drawing here is like to the theory of NP completeness in combinatorial optimization. We're able to, not me, but establish this class where we sort of group together all the hard problems, showed that there's one that essentially captures really the hard problems in all of them. And sort of here is do a similar one, sort of a similar characterization for these explicit construction problems. And I'm going to explain very shortly how I'm actually formalizing explicit construction problems as a computational task. But for now, this is sort of the high-level goal of what we're trying to do. So, what are some properties we want of like a complexity class? Is that it should contain the interesting problem to understand, and ideally, it should be an interesting complete problem. Maybe these are some minimal things we would want from a complexity class. Is that, the point, we're not just defining a class for the sake of it, but like hopefully it'll really shed some light on like what are the core most different problems in a class. So just before I start to define more formally, a second motivation for this, beyond like specific algorithmic applications where we'd like to have better constructions of expander graphs or error correcting codes and these concrete combinatorial objects, a second motivation comes from sort of circuit complexity and the theory of lower bounds. And so this came out for Erdős's paper and is like the second major example of the probabilistic method. Second historic major example. And this was a paper of Shannon, paper where he showed that this Boolean functions, which require Boolean circuits of size exponential in the number of input wires. And the proof, again, is of this style where we choose a function uniformly that this happens with high probability. And the point is that sort of explicitly constructing of a function meeting Shannon's like non-constructive argument is like essentially the same as proving a strong complexity lower bound, a circuit complexity lower bound. And this is sort of one of the main essential topic of complexity theory, is to prove like explicit lower bounds for computational problems that we're interested in. So so just to be a little more formal, you can show, for example, that if there was sort of a polynomial time algorithm that could print out a truth table, so we think of like writing down the whole truth table of the Boolean function that has length 2 to the n. If we could have an algorithm that could print out an example meeting Shannon's non-constructive argument in time that's polynomial just in the length of the whole truth table, and that it has high circuit complexity, this is equivalent to a certain circuit lower bound saying that exponential time does not have polynomial sized circuits. And without getting too much right now into the details of what that means, this is sort of an important precursor to proving what we really want to prove, that NP does not have polynomial sized circuits, which would tell us that P is different from NP. So sort of proving these circuit lower bounds for these very large classes, exponential time classes, is like a really important sort of problem in complexity theory. That's sort of we need to solve this before we can get to like the really hard problem. Well, they're both hard, but the even harder problems of proving lower bounds for NP. So this is sort of another motivation for this problem. This is maybe actually the more important, or the original motivation from when I was looking at this problem. So getting back to this, I said we want to establish a complexity theory for explicit construction problems. How do we formulate them as a computational task, like a well-defined one? So the idea is that in each of these cases, I said, I gave you some definition of like a good combinatorial object that has some like nice property. If it's in each case, we can sort of imagine the object in question is like described by a certain number of bits, right? If it's a graph on t nodes, it's t squared bits. If it's a matrix, it's m squared, where m is the number of dimensions. And so in each of these cases, we have some definition of like a good object. And the explicit construction problem is that we're given as input the length of the object, and the goal is to output one example of a good object, which has that description size. So if you're not familiar, the reason I have 1 to the n on the left is this is just a convention in complexity theory that we always measure the sort of input size as the length of the input string. So the only point here is to say that this is kind of an unconventional problem where the input is really just a number specifying the length of the object we want. And we're allowed to run in time that's like polynomial in the length of the object. So the input is like sparse. We're not given like a graph or a circuit or something like this. We're just given a number specifying the length, and we're supposed to print out something of that length. So for the example, just to be concrete, for Ramsey graphs, the input might be 1 to the n. We're supposed to print out an n by n matrix, which is Ramsey. In the case of hard truth tables, here we're given as input a length which happens to be a power of 2, which is 2 to the k. And where the goal is to print out a length 2 to the k truth table of exponential in little k circuit complexity. So in this case, on the bottom one, I would be measuring the complexity with respect to like 2 to the k with respect to the length of the whole truth table. An efficient algorithm with for this would be a run in time polynomial in 2 to the k. Does this make sense to everyone? Like how this is just how I'm parameterizing the problem is sort of the parameter is the whole description size of the object that you want to produce, and the goal is to produce one. And so for all of these problems, like I said, the problems we're interested in, there's some non-constructive proof that says there always exists a good object of every size. So what that means formally is that I defined, the explicit construction problem, is what's called a total search problem. So this is a problem that always has a solution on every input. And a little bit more than that, like I said, we have actually not a specifically probabilistic method proof, and the proof actually gives us a little bit more. Not only there exists a good object, but if I choose one at random, it has a very high probability. So actually, this is not only a total search problem, but it's one that typically has many or that has solutions. This is sort of these phenomena of total search problems have been encountered and studied a bunch before. And typically they present some difficulty in like defining interesting complexity classes and classifying problems. And sort of an approach to how we should classify total search problems was initiated by mainly this paper by Papadimitriou from '94 and also earlier one with Yanakakis and Johnson, where the idea is really to sort of, if we have this class of problems that are all total search problems, and we want to sort of identify like maybe a complete problem within this class, a good candidate is to try to look at the actual non-constructive proof that shows that these problems are total. So sorry, let me back up a little bit. When it's total, that means that for every instance, there's always a solution. And typically this is shown by some theorem. Like in the example of explicit construction problems, the fact that always a good object is shown by some probabilistic method proof. In general, there's some usually non-constructive proof which shows that every instance has a solution. And so the idea is that we're going to identify like what is the core non-constructive step in this existence proof, and then define a computational problem that sort of isolates that core step. And we're going to take that computational problem to be our sort of complete problem, like the equivalent of SAT, the role that SAT plays for the class NP. And then once we have this complete problem, we sort of place together all the problems that reduce to this, and hopefully we identify like an interesting cluster of computational problems that we call a complexity class. So the idea is we want to do this for these explicit construction problems, and I'll explain like the approach we're going to take now. So imagine that we have like some definition of a good object, maybe, sorry, I know this is a very abstract terminology, a good object, but yeah, maybe, some n-bit, like we can think the example of Ramsey graphs. We have the whole set of n-bit strings, some of the, which all we think of as representing in some sense like a graph. We have some definition of the ones that have some property we want that are good. And we have some non-constructive proof that tells us that the vast majority of them are good. In other words, if I were to circle the bad ones, it would be like a very, very small subset of the Boolean cube. So then, by definition, if this set of bad ones is at most, a half of the set of all possible strings, then, information theoretically, it should be possible, or it is possible, that I can cover the set of bad strings by a small set, by, in particular, a set that's half as big. So, right, all I mean here is that if I have, a small set of size 2 to the n minus 1 inside of 0, 1 to the n, then by definition, there's some function mapping, strings of a smaller length onto strings of length n, which should cover all those bad x's. And sort of like the key observation here, or sorry, yeah. So, and just to say is that if I could, construct this function f in some explicit, efficient way and present it to you, then solving the explicit construction problem would now reduce to the following problem. I just want to find a single example of some x which lies outside the range of this function, right? Because the way I've defined, the property I've defined this function to have is that it covers all of the bad ones. So if I can find something outside the range, it must be a good one. Yeah, and so sort of the key observation is that in many of these probabilistic method arguments, if we sort of unroll what the argument is doing, they actually sort of yield this explicit function f, which is able to sort of describe all of the bad instances using a smaller number of bits. And so in many of these in many of these probabilistic proofs, we're able to extract from the proof an explicit example of this function f, which is polynomial time computable. And so it can be described by a circle.
Sorry.
Yeah.
So I'm catching this question a little bit late. I'm afraid there is a question in the chat. Are we going to consider the complexity of verifying solutions?
I will get to that. Yes. So I'll get to that shortly. I think shortly. So let me
thanks.
So yeah. So the point is, if we can if we get to this situation with our explicit construction problem, where we've sort of shown that the set of bad x's is small by exhibiting explicitly a function which covers all the bad x's using strings of a smaller length, then I can define this problem where I give you the function f, which has fewer input wires than output wires, and it has a property that anything outside its range is a solution to your problem. So from this, we can define the following problem, which is called range avoidance. So in this problem, the input is a Boolean circuit that has fewer input wires than output wires. And sort of the solution that you're seeking in this problem is a string y, which is in 0, 1 to the n, that's not in the range of this circuit. So you can see from the definition from the pigeonhole principle that this problem is a total search problem, because any function that maps a smaller space to a bigger one cannot cover the whole codomain. So the range. And also you can see from this problem, actually, it shares this sort of common property that a randomly chosen solution is correct with high probability. So if I choose a string from 0, 1 to the n, that is at least twice as big as 0, 1 to the L. And so I have probably at least a half that I'm outside the range. So the sort of the main thesis of this work is that this is the right problem to be able to capture the complexity of most of the interesting explicit construction problems. So all of the problems I mentioned, plus some more I didn't mention, you can sort of reduce the explicit construction problem for all of these interesting combinatorial objects in polynomial time to this range avoidance problem. And I'm just remembering, so let me slightly answer this question, because I remember now it might be a while before I get to it. I thought it was going to be the next slide. Is that, I will get to this in more detail later, but something you can observe here is that for this type of problem, verifying a solution is not necessarily a polynomial time thing. We need to check that y is a valid solution for this problem. We need to check that it's not in the range of the circuit, which could be, in theory, an NP-hard problem, because I need to say, for all possible preimages, do they map to y? And that property is also, before I defined this range avoidance problem, if you looked at any of these particular problems, most of them, it's actually NP hard to verify that the sort of given object is good. So I'll get more into this later, but the point is that this is a property that's shared both by range avoidance and by all these sort of motivating problems that we define range avoidance in order to understand, is that they happen to be problems. A randomly chosen solution is good, but verifying a solution is actually not easy. So yeah, I was going to get to that later, but I should answer that because somebody asked. So anyways.
Ask a question about that, Oliver.
Yeah.
So I guess in some of these instances, at least verify that a random y is a solution. So like I guess for expanders, you can verify that a random graph is an expander. Is there some sort of understanding as to, are these properties special in some way?
Oh, you mean like, okay, yeah, I guess you would phrase that. You're saying that there's like a natural property against expanders or whatever. I guess that's the way you would technically say that. So yeah, I guess that's how we would, for these problems, we would, the technical term for that would be that there's a natural property for them. Okay, well, I said that testing these properties would be hard. I meant that in the weaker sense. Just, you know, in general, determine, okay, well, the first one, this is a famous open problem if for circuit complexity, verifying circuit complexity, but for like rigid matrix or Ramsey graphs or things like this, like in general, to test like parameters such that it's a Ramsey graph, or, you know, the best parameters that you read are NP hard problems. The question you're asking is different. People who aren't is like, it is true that there's some testable property which implies being an expander and is satisfied by a random graph. Not all of these problems. I would say that's a property, like, once we get that, we've sort of reduced the complexity of the problem. So for most of these problems, we don't have that. And maybe a concrete way to say that, to see that, is that if we have what you're describing for expanders, that automatically gives you a p to the np. Sorry, for everyone else who not asking this question, it's okay if you're not following what I'm saying right now, but I just that automatically gives NP oracle construction algorithm, because I can if I have this polynomial time testable property, I can like use an NP oracle to construct something that satisfies it. So for these problems where we haven't made as much progress as we have with expanders, it's already open to give a p to the np algorithm, and so for those we wouldn't have these natural properties like you described.
Thanks.
Cool. Yeah. So yeah. Anyways, but that was that. You didn't follow what I just said. That's totally fine. Yes. So what I was saying is, yes. So like the main first result is that we can reduce sort of all these explicit construction problems to this one canonical range avoidance problem. And the proofs are all kind of straightforward. Essentially, you work through the standard probabilistic method argument, and you just sort of note that at each step, we can sort of turn the argument into a constructive encoding. So before, we argued sort of just with counting that the set of bad instances has small mass. And now we're going to make that a constructive argument by specifically showing that any sort of bad object can be explicitly described using a smaller number of bits in a way that I can recover the object efficiently from its small description. So the way that these reductions work. So I'm going to go to the example where I already defined what the object is, which are these Ramsey graphs. So remember the definition of a NK Ramsey n by n Boolean matrix, so that every set of k rows and k columns, if I look at the submatrix, I should have both ones and zeros. And like I said, if k is like just a bit larger, and these types of graphs exist, and it's an interesting problem to construct them. The idea is very simple. We're just going to do that. You know, if it's not a Ramsey graph, then there exists some pair A and B, so that this rectangle is entirely covered with zeros or entirely covered with ones. And we're just going to use those A and B to sort of compress this whole matrix to have a shorter representation. So what is the compressed representation? We just literally specify B. We specify the value, right, that matrix has. Either it's all zero or it's all, call that value V. And then we just specify the values of the entries of the whole rest of the matrix. And so then I can define some instance of range avoidance for some F, which is going to take those parameters A, B, V, and M, which are going to be encoded by some bit string, and then output a matrix M in the following way. We construct, so we just look at the entries A, B, we fill all of them in with the value V, and then we fill the remaining entries using the stuff specified in squiggly M. And the point is, like, by definition, if a matrix is not, then there exists some A, B, V, and tilde M, so that this procedure reconstructs matrix. And so the only thing that, like, the number of bits of this description is smaller than the number of bits we're outputting, which is n squared. And you can just count this up, and provided I choose the parameters as Erdős's proof, if I choose k a bit larger than log n, the number of inputs will be strictly smaller than the number of outputs. And so we'll actually have an instance of range avoidance. And like I said, by definition, anything outside the range of this function is a Ramsey graph. So any solution to this range avoidance problem is going to give us an example of a Ramsey graph. If I went too fast for anyone, please, like, slow me down or feel free. So yeah, so that's our first example of reduction. Most of them, with, I'm showing you sort of the two simplest ones. But the second one that's going to be really important is this problem I mentioned of constructing hard truth. So in this
Oliver, just to sort of the double check. So what you're saying is basically first identify this monochromatic big rectangle, and then we fill it in. And then sort of, I just, all the other bits are just in some, order, I don't know, row by row, column by column. Then I just fill in the other bits. And then I just count, and I see that that was like smaller than n squared is what you're saying.
Exactly, yeah. So I just count, so specifically A and B take like log n choose k bits. I'm skimming over something. You can prove that there's an efficient encode like a subset of n of size k using the optimal number of bits log of n choose k. So this is something you need to prove it's possible. I need 2 times that many bits to specify b. Specify the value, and then n minus k by the rest of the matrix, because A cross B is going to take up k squared entries. And then exactly like you said, if you just count up these numbers and a little bit larger than log n, you'll get that all of these is less than n squared.
Okay. Maybe this is completely. Do I care about the efficiency of the encoding at all? It's not clear that I would. I'm just.
So great question. So for this problem, we don't care about the efficiency of the encoding at all. And we can think of it like a non-deterministic thing. We just need to show that every bad object exists an efficient, a succinct description. What we do is the efficiency of decoding. So there's an efficient polynomial set we can construct, which is able to decode the small description of every bad. But going from the bad object to the small description can be we don't need a computational efficiency for this. And so this is actually going to, so this will come up, first of all, or second half of the thing, where we do wondering about problems where we have an efficient encoding procedure. I'll go back to question of, for these problems, we test if an object is good. If we had a proof like the stronger property that we also do the encoding efficiently, I would be able to also, test if the object has the good property by seeing it recovers from its description. And so for some of these problems, we strongly believe that there's no proof which is constructive in the encoding and decoding direction, precisely because it's hard to test these properties. So the prime example is the top here, truth tables of high circuit complexity. So you can show, for this problem, what I show is that there is a way that has proof that has an efficient decoding procedure. But if there was a efficient encoding procedure, then there would be one-way functions. This is something that's strongly believe in this case that it's only the decoding procedure that can be efficient.
Okay, thanks.
Yeah, no problem. So yeah, the problem that I just mentioned is in this problem we're trying to construct truth tables of Boolean functions which have high circuit complexity. Something to keeping in mind with this problem that's a little annoying is that like n here is the number of variables of the Boolean function in question. Really, the input-output size of the problem we think of as being 2 to the little n, which is the description size of the whole truth table, like written out, f of the first string, f of the second one, all the way to 2 to the n. So the problem here is we're given sort of 2 to the n as our like sort of input parameter, and our goal is to print out a truth table of length 2 to the n, which describes an n variable Boolean function of exponential circuit complexity. And so for this problem, the reduction is extremely simple. Again, we want to show that all of the that have small circuit complexity can be sort of described efficiently. Well, how do you just take the description to be some bit string describing the small that computes the function, right? So if a truth table T, I guess I didn't write the name of the truth table is T, if it has a circuit of size significantly smaller than 2 to the n, then I can sort of describe this using strictly less than 2. And then I can recover the truth table from the circuit by just evaluating the circuit on every bit string. And if we remember sort of the complexity is measured with respect to 2 to the n, so enumerating over the n bit string is considered efficient with respect to the input size of this, right? Because we're just trying to produce a hard truth table in time that's polynomial the size of the whole truth table. So I have a small circuit. I can define some instance of range avoidance, which just computes the circuit on all possible inputs. Right, table is, and any with a small circuit will be in the range of this map F. Did that make sense? Sorry, and what I didn't mention is that if you choose S to be less than 2 to the n over, so you can do 2 to the n over just n, then that's the parameters for this argument works. And this is known to be tight as a circuit of basically that size, exactly. Not exactly, but almost. So, yes. So just to remind sort of where we are right now, define this problem, range avoidance. And what we're able to show is that, so I gave 2 examples, but we're able to show for this sort of all of these problems, essentially these explicit construction problems that come up naturally a lot in TCS, sort of it's, for most of them, it's very easy. For others, it's, only slightly easy, but still pretty easy to reduce them directly to this problem, range avoidance. So this gives kind of a, in my opinion, like indication that this is probably the right sort of exact complexity class to place all of these problems in. So before I get to the sort of the next result about this class, I want to like talk. Someone asked before, is this problem, can solutions be verified? Like I want to zoom out, understand where in the sort of hierarchy of complexity classes this problem seems to lie. So just writing it down in the corner again, the input is this circuit that's extending the number of bits, and we want to find something outside the range. And the first observation, which was basically someone's question before, is that this problem is not obviously like an NP search problem. So if somebody shows me Y as a candidate solution, I can't clearly verify that it's a solution because I would have to check for all possible inputs that they don't map to it. So this doesn't mean it's not an NP. The situation's unclear, but it's not clearly an NP. So what can we actually concretely say about it? Well, in terms of upper bounds, sort of what we can say, sort of the most precise thing we can say easily is that it has what's called a ZPP to the NP algorithm. So what do I mean by this? Well, we said before, if you just randomly choose a candidate solution, it's correct with high probability. Now, if I had the ability to test if it was a solution, I could make an algorithm that just randomly selects and keeps testing until it finds a solution. And the complexity of testing a solution is about that of SAT. Because, if you say testing whether Y is in the range of the circuit, we can reduce that to like a satisfiability problem. Is just, does there exist X, which maps to it? Remember that C is polynomial sized circuit. So with that, if I had access to a SAT solving oracle, I could solve this problem with a randomized algorithm that always eventually finds a solution with high probability. It only takes a polynomial number of steps. And so this is what we call a ZPP to the NP algorithm. So this is a randomized algorithm that is sort of in unit time can solve instances of SAT. And that's basically the best, like, easy upper bound we can put on this problem. In the other direction, we know that it's, sorry, in terms of like lower bounds, like what is this problem at least? Well, we know it's at least as hard as all these explicit construction problems, but in terms of like more standard complexity classes, we can say that it's at least as hard as BPP. So what I mean by that is, if you don't know what this class is, any binary value decision problem, so like a standard decision problem, that's decidable in probabilistic polynomial time, we can reduce that problem deterministically to range avoidance. So this is non-trivial because it's a very important open problem. We don't know whether BPP is the same as P. In other words, whether we can always remove this from decision problems. And so what we're saying here is that, this problem is at least kind of as hard as the, solving this problem in time is at least as hard as the general problem decision problems. And so the claim I wanted to make by bringing this stuff up is that sort of, we said on the left, we know that this problem avoid is in what I called ZPP to the NP. And I claim that sort of already a very interesting question about this problem, which is kind of non-standard. Before I was comparing this to trying to build an analog of NP completeness, where normally the type of reduction is a polynomial time reduction. But I claim for this problem, it's already interesting to study things under this stronger notion of reduction called a P to the NP reduction, which is where I can have a polynomial time algorithm that can solve SAT in unit time, which is, obviously not a realistic model of computation, what we think. And my claim here is that it's already would be extremely interesting to improve this upper bound of ZPP to the NP with the upper bound of P to the NP. And what are some concrete reasons? Well, it would imply sort of a bunch of breakthroughs in complexity theory. The first of which it would imply, you don't have to know specifically what this means, but it would imply super polynomial size circuit lower bounds for a class which we don't know how to prove circuit lower bounds for. This is sort of the one on the left, that's a frontier problem in circuit complexity. And on the right, like I said, we know that BPP, all randomly solvable decision problems are reducible to range avoidance. And so if we could improve this upper bound for range avoidance, this would imply that BPP is in solvable, every problem solvable with randomness can be solved in polynomial time with an NP oracle, which is surprisingly, that is no do that. We believe actually that everything in BPP is in P, can be solved just deterministically, but it's a sort of a frontier problem in the subject of randomness. Derandomization is to show this inclusion, that we can do it with an NP oracle, and it's not known. So this kind of weird, the point of this slide is just to justify that sort of, it's already interesting to study this class of problems. Instead of like with NP completeness, the standard notion of reduction is a polynomial time reduction. We look at this stronger notion of NP oracle reductions, or P to the NP reductions. And the point being, just that it would already be a sort of a huge breakthrough for a lot of the problems in this class to obtain an algorithm like this. And this, I mentioned this specifically for like, truth tables, or in other words, proving circuit lower bounds. But this also holds for, if we look back at, a lot of these other problems which are unsolved, like rigid matrices or randomness extractors, that previously in the literature noted that sort of the barrier for these classes is like, not only can we not explicitly construct a rigid matrix, but it's not clear how to do it even with an and so these were already sort of a view on these problems that people had prior to this work, that sort of the barrier class that is the difference between what's easy to do and where you need sort of a non-trivial approach, is already happens in this class P to the NP. Happy to clarify anything if that was confusing. Please feel free to interrupt. So, okay, with that in mind, we can sort of improve this picture of this complexity class significantly in that we're able, if relax our notion of a reduction from polynomial time reduction to P to the NP reduction, then one of the problems on this list actually becomes a complete problem for this class. And so we've sort of satisfied, like I said, the two really important properties of a nice complexity class that really captures a class of problems is that, you know, it should contain all the interesting problems you were curious about, and that one of those interesting problems should be complete. And the problem that's going to be complete is the first one on this list of constructing truth tables of high circuit complexity. So, so that's what I'll state now, and I will prove this later in the second half, but not right now, is that if we take epsilon to be any fixed positive constant, then we can reduce the range avoidance problem to the problem of constructing a truth table which has circuit complexity 2 to the epsilon times number of variables. So this problem, so this theorem is from my paper, that's the K21, but also it influenced very strongly, and more generally, a lot of this work by a work in proof complexity, specifically bounded arithmetic by Emil Jerzebek from much earlier, which I don't want to get into the details of that because it's very hard without context to explain what he was doing, but he studied a lot of these very similar problems in the context of bounded arithmetic, and this specific theorem is very similar to sort of a proof theoretic result of his from 2004. So that's where that combined citation is. So anyways, yes, so what this theorem is saying is that we can reduce this general range avoidance problem if we're allowed these more broad reduction p to the np to the specific instance of range avoidance of constructing these hard truth tables. And so, yeah, like I said, this means that this is like the complete explicit construction problem amongst this class, provided we have this stronger notion of reduction. So yeah, in particular, this says that if I can sort of make the probabilistic method constructive just for this one problem, then I can sort of simultaneously improve it and make it more constructive for all of these problems. The caveat, again, being that this is only for p to the np algorithms. So if I have a p to the np algorithm, then that automatically implies p to the np algorithm. Still, polynomial time algorithm is the actual like useful one. But you know, it still says something sort of interesting about the structure of this class of problems, even though we've now moved to a model of computation which is not realistic. Like physically realistic.
If you believe in the power of modern SAT solvers, right? Then it's like you have
yeah,
P to the NP.
That's true. Yeah, exactly. So with the SAT solver, yes, you could have all of these precisely. So yeah, so just to like kind of unroll what all these things mean. Well, if you remember way at the beginning of this, like one of the motivations for implicit construction problems related to constructing hard truth tables is that efficiently constructing a hard truth table is like equivalent to proving that a certain complexity class requires large circuits. So in the case of p to the np construction specifically, we can show that the following two are equivalent, and it follows essentially just from the definition that it won't be obvious given the amount of definition I've given you, but that the two are equivalent. One is that there's a p to the np algorithm to construct hard truth tables, specifically of hardness 2 to the epsilon n for epsilon. That's equivalent to saying that this complexity class, which I haven't really defined formally, called e to the np, requires exponential sized circuits. And the point is that this class e to the np is kind of the barrier class where for any significantly larger complexity class, we can very easily prove a circuit complexity lower bound. In this class, we don't know how to prove it, and it's sort of considered sort of the really strong barrier of like the next class that we breach to move our circuit lower bounds closer and closer to NP. I mean, this class is very far from NP. If you are familiar with these things, we're very far from solving problems like NP does not have polynomial sized circuits, and this is specifically sort of the point at which we're stuck, essentially. So yeah, these p to the np constructions for this explicit construction problem are equivalent to, as a statement, to this circuit lower bound. And now this completeness result says that this p to the np construction for some epsilon, if and only if this range avoidance problem is in p to the np. It has a deterministic NP oracle algorithm. And so this gives us an equivalence that we have this complexity class of all the problems reducible to ranges, and we can say that and the only upper bound we can put on it right now is like Z NP. And we can say that collapsing this class down to P to the N is possible if and only certain circuit lower bound holds. So we have a cool situation where we have this complexity class, we can characterize actually how hard it is precisely by a circuit of a different class. So something to note now that I've gotten to this point is that the thing on the upper side that this class requires large circuits is very widely believed to be true. So it's implied in particular if you believe that some NP complete problem requires 2 to the omega n circuits to solve, then it would imply this. And I think people really strongly believe that sort of thing. Like if you believe in that strong exponential time, and you think that it holds also for non-uniform algorithms for circuits, then this would be true. And so this equivalence says that really the belief is that range avoidance does have these improved algorithms, these NP oracle algorithms. So this is a bit different. Like I said initially, that maybe the goal here was a complexity theory, give us complete problems for these explicit construction class. It's a bit different. I gave the analogy to the theory of NP completeness, but it's a bit different because there the point is to prove that problems are hard, and we think that that's the end of the story, and they are hard. For these problems, I guess we established this sort of completeness phenomenon, and then maybe the most interesting takeaway is that we can use it to collapse all of these problems to a lower complexity class. If we take away whatever our specific opinion on these things are, we just have this equivalence, which is nice. And sort of the last thing I wanted to say here is that using this equivalence, we can show one more kind of thing in circuit complexity, which is a bit interesting, which is, so on the left-hand side, on the bottom and the right-hand side, the bottom and the right, I have this equivalence, which I stated, that, a circuit lower bound little o of n, or 2 to the omega n, is equivalent to range avoidance being in P. If you recall, the problem that we showed, the construction of hard truth tables that we showed reduced avoidance actually has a stronger circuit complexity parameter than just 2 to the epsilon n. We're able to show that construction of truth tables of complexity 2 to the n over n reduces to range avoidance. And so by the same equivalence I mentioned, this is going to say that if range avoidance is in P to the NP, then actually we can prove a circuit lower bound, which is better than just 2 to the omega n. We can prove a lower bound that's 2 to the n over n. That's possible. And so if we combine these two equivalences, we get that this class e to the NP has a kind of dichotomy theorem for its circuit complexity. So we can show that either some language in this class attains the maximum circuit complexity, 2 to the n over n, or every problem in this class has a sub-exponential circuit complexity, to the little o of n. So this is kind of just a curious little that we don't really know anything like this for other complexity classes. It's a bit weird, and sort of using this range avoidance problem and the reductions to and from it, we can show that this complexity class has the property that its circuit complexity is either the maximum or significantly smaller. So I think that, so that concludes what I was going to say for the first half of this. And just to summarize things a bit, the point of what I did was we sort of gathered together all of these explicit construction problems, and we showed that they fall into this complete problem called range avoid. And the second thing is we showed that essentially the most important problem in this class is actually as long as we sort of move to a more broad reductions. And finally, that sort of this whole class collapses to P to the NP if a certain circuit lower bound holds. Sort of characterize the derandomization class by a specific complexity assumption. Yes. So yeah, that sort of the main point of what I wanted to get across here. I think there is a break, and then I will say some more.
So thank you so much. Clapping on the behalf of the audience. There are also some hand clapping emojis in the chat, or sorry, in the participant window, I guess. Great. So before we take a break, any questions at this point? Anyone in the chat, or if anyone wants to unmute and ask anything?
I have a question actually.
Yeah.
I've seen like in a similar kind of flavor paper that is like I think the power of natural properties is powerful. That they are proving a result substituting like the assumption or over like the circuit lower bounds with indistinguishability obfuscation. Would it be relevant to try to assume something like obfuscation in this context?
I'm not sure. So I think I know what paper you're talking about, but I forget about the indistinguishability obfuscation. I think usually in these, so there are a few of these results that I was going to talk a little more in the second half of, like hardness, randomness, they're called, where we can de-randomize a certain problem, assuming some circuit complexity. Typically at these circuit complexity assumptions, I would say, are like qualitatively of a kind than like cryptographic assumptions. Sorry, I don't know if I have a. Okay, so now I think about it, there are some in the what's called this de-randomization literature by Chen and Tell, which actually do look at, so not indistinguishability obfuscation, but the one-way functions, and they show certain de-randomization is possible, like better de-randomization is possible if we assume the existence of one-way functions. So sorry, I went in a circle, but now there are more examples of what you're talking about. They're a bit different than what's going on here, but I would say they fall like broadly under the same umbrella of what we would call hardness randomness theorems, which say, assuming some circuit lower bound assumptions, we get upper bounds. The upper bounds are usually for problems that are solvable with randomness and not solve them without randomness.
Okay, thank you.
Yeah, cool.
Any other questions before we?
Yeah, sorry. So Oliver, I had a question in general. So you connected this with the existence, I guess, the probabilistic method or explicit construction questions.
Mm-hmm.
So we have lots of explicit construction. Is there any way of kind of seeing as subcases of the, or seeing at least a good number of them in this way? Does that help to kind of?
Wait, sorry, you mean the ones that you're saying, the ones that we already have solved?
Yeah. Does that give us an idea of what kind of problems of this kind we can solve?
That's a good question. So, all right, maybe can I rephrase and see if this is what you mean? Are you saying, can we describe some special case of range avoidance which we can solve and which explains a certain class of problems we have? So that's a great question, and I don't know of an example of that. A related thing is that people have been studying recently restricted versions of the range avoidance problem, where we restrict the circuit to be of some very simple form. And they've shown, for example, that some of these important explicit construction problems that are still open reduced to very simple case of avoid. So like one case is where each output bit only depends on 4 input bits. Maybe you're familiar with this. Yeah, so that's similar to what you're saying in terms of looking at restricted cases, but no, I don't know of any subclass of range avoidance which has been solved other than, okay, I can think of one, which is that this case of each output bit depends on only k input bits. If the number of output bits is like more than n to the k, then you can solve it. This has been proven, and this is the only, and I don't know of any explicit construction problems that reduce that. So I think it's basically open to answer your question. Yeah.
Okay, so maybe this is a good time to take a break. So we're back after the break, and Oliver has promised to tell us more about range avoidance. So now you can't avoid it.
Wonderful. All right. Yeah, I hope everyone had a good break. In this like sort of second half of things, I'm going to talk about give you some more proofs of things on sort of 2 results I'm going to focus on. One of them is going to be that result I said before, that the constructing hard truth tables is complete for this range avoidance class. But we're going to prove that at the end, because first we're going to prove something which is like a bit more complicated version of the same argument, which is addressing a problem that I think of as like a cousin to the range avoidance problem, which I'll try to explain why I think it's interesting to study. And we're going to be able to prove some sort of weird and kind of interesting things about it. Before I get to that main topic I wanted to talk about in this half, I do want to mention just one thing, that it's a very significant update on this problem recently that I would be remiss not to mention anywhere in this talk. If you recall, what I said before is that the upper bound, sort of the easy upper bound we can give for this problem is a ZBP to the NP. So yeah, the idea is we sample a random solution, use the NP oracle to test it. And one property of this sort of easy algorithm for the problem is that you can observe that the solution we find with this randomized algorithm is going to vary with the internal randomness. So in particular, the solution I output for a fixed, instance C is actually going to be a uniformly random amongst all possible solutions, right? Because I just uniformly sample and reject basically whenever it's not a solution. In a very recent sequence of two papers came out, one very close after the other, it was proved that we can put an unconditional stronger upper bound in this problem of what's called a pseudo-deterministic ZBP to the NP algorithm. So this is going to be an algorithm, again, it's going to be a randomized algorithm using an NP oracle, but it's going to have this very interesting property that the solution that gets output by the algorithm is one fixed solution that depends only on the instance. So for each instance C, there's going to be one fixed special solution depending just on C, and a randomized algorithm which with high probability outputs that one fixed solution across all of its random coin flips. And so this was proved in a combination of two papers, one by Chen, Hirahara, and Ren, and then a follow-up by Li. And it has some very cool implications. In particular, it proves like new circuit lower bounds for these exponential time classes. So for the class that's like the exponential analog of ZPP to the NP, this result proves that this class has exponential circuit complexity, which is not known for a very long time. So anyways, I think this is a very cool result. And this applies like for all of these explicit construction problems I mentioned. Now we know this, non-trivial thing we didn't know before, which is that I can solve all these problems in what's called pseudo-deterministic ZPP to the NP.
Is it possible to say anything about, because it really, as you said, I mean, the obvious way of doing it is like you'll get a uniform sample. Like, can you say anything about the magic that makes it pseudo-deterministic?
Yes, so there are two magic ingredients in it. One is going to be an argument involving a tree, which is going to be similar to the trees that I'm going to show you in later slides in this. So without saying too much more, there's going to be arguments that one half of the argument is kind of similar to what we're going to see in the rest of this talk, of certain techniques for analyzing the range avoidance problem by composing the range avoidance instance with itself many times and building a sort of tree. And you'll hopefully understand a little more what I mean when I get to the rest of this half of the talk. And the second half is going to use some algorithm discovered by Tsai about 20 years ago, that what he showed was that this class S2P is contained in ZBP to the NP. And that's, I know off the top of your head, maybe S2P is a really weird complexity class that doesn't come up a lot. But sort of there's two steps to the argument. What these papers show is that the range avoidance reduces to this class called S2P. And that part of the argument uses these tree things, which you'll see shortly. And then to get the pseudo-deterministic ZBP algorithm, we use this result of Psi. And the place where the randomness comes in is it uses some tricks involving universal hash functions to do approximate counting. So I don't know if you're familiar with this stuff, but there are these sort of known techniques that were invented many decades ago that you can, for example, approximately count the number of solutions to a SAT formula, or you can approximate any sharp P function using a randomized NP oracle. And the sort of technical details of this involve universal hashing. So that part of the argument, those sort of techniques come into this. And there's like a new part of it, which is very specific to the range avoidance problem. But I don't know if that really gave you an idea at all, but that's sort of the best explanation I could give. And it will be somewhat similar to the proofs that I'll show you shortly.
Okay, fair enough. Thanks.
Yeah. So anyways, I think this result is like very, very cool. And I'm not going to present it in any more detail, but I just, I wanted to say something. Also, just a note is that the second of these two papers, this is by Lee, is extremely simple. Like, I don't mean that at all in a bad way. It's like a remarkably elegant, simple proof that is not so like you could follow it. And I highly recommend to anyone interested to read it because it's super cool. I mean, the first paper is also very cool, but it's much more technically involved, and Lee kind of simplified everything a lot. So anyways, highly recommend if you're interested at all. It's super cool proof. But now I'm going to move on to some other aspects of this problem. So what I'm going to talk about here, it may seem like a little bit of a non sequitur, is I'm going to talk about a problem which I'm going to call like a cousin of the range avoidance problem, which I'm calling the lossy code problem. And this relates to a question somebody asked me, I forget who it was, in the last part of the talk, which was when we do these reductions to range avoidance, we have sort of this decoding procedure which has to be efficient, which we said any bad object, I can describe it with less bits. I don't care about the efficiency of giving the small description. What I care about is the efficiency of decoding the small description. And what this problem is going to correspond to is situations where we have a sort of a probabilistic method proof which is efficient in both directions. So given a bad object, we can efficiently compress it to a smaller description and then efficiently sort of recover the original object. And so I'm going to define a search problem which is sort of analogous to range avoidance when we have a probabilistic method proof which is sort of efficient in both directions. So in this problem, we're given sort of, you can think of the top half of this, the function d is a function mapping fewer bits to more bits. So that's the same as range avoidance. But now below that, I also have a second function which maps the larger number of bits to a smaller number. And sort of what the pigeonhole principle tells us in this case is that, if I sort of compose these two functions, then the composition can't be the identity function. I have to like lose information if I go from n bits to a smaller number and then back to the original n bits. So this defines like a total search problem, which is find some witness that the composition of these functions is not the identity. Or the way I like to think of it, I like to think of like C and D define like a compression scheme that compress any n-bit string down to n-1 bits and then lets you recover it. And the goal here is to find some string which is incompressible. Because we know in general, you can't have a lossless compression scheme using that always compresses to fewer bits. So that's why I call it the lossy code problem. The idea is, you're given this compression scheme and you want to witness the fact that it's not a perfect compression scheme. And so again, what can we say about this problem? Again, it can be solved with randomness. If I choose a candidate solution at random, it's a solution with high probability. But unlike the avoid problem, this is an NP search problem now, because I can verify that a given X does not map back to itself under the composition. I can verify that very efficiently. I just feed it through.
We're assuming that these boxes are efficient. Maybe you said this already. So
yeah, exactly. Yeah, maybe I didn't say that actually. These are given to us by like Boolean circuits or polynomial time algorithms. Yeah, Boolean circuits. So exactly. So evaluating these are efficient. And so we can see, first of all, that it's potentially easier than avoid, and also it's very easy to see that it reduces to avoid. If you look at this picture and just ignore C, the bottom per circuit, if I solve, then D looks like an instance of range avoidance, and if I can solve range avoidance for D, then that's automatically a solution for this for this restricted lossy code problem. So if I just forget about C, this problem becomes like range avoidance. Then it's like a potential easier problem. Than for avoid, which has some very clear motivations because all of these interesting problems reduce to it. Sort of my motivation originally for looking at this, maybe the primary one is that it's sort of a toy version of avoid that's sort of an intermediate derandomization problem between, I'll explain more what I mean by this, but between sort of derandomizing avoid, which is maybe the goal there is this P to the NP derandomization. And, this problem is like falls more into an NP search, is an NP search problem. Potentially we could derandomize it down to P. Potentially we could derandomize it under sort of different assumptions than range avoidance. and we could learn something about range avoidance by studying it. But a real good motivation would be to show that there are interesting explicit construction problems that sort of reduce to this in the same sense that they reduce to avoid. On this front, I have a lot less interesting stuff to tell you. I will say the one sort of strongest example is this unfortunately unpublished reduction that Ian Mertz and James Cook showed to me, which I can explain to anyone if they're interested. But a certain problem involving simulating catalytic space algorithms is an open derandomization problem that you can show reduces to this weird problem I've defined. So that's one motivation that should be published somewhere, but it hasn't been. And another one is that there's some weak connection to constructing primes, which is another open problem in explicit constructions. But maybe the strongest last motivation is like what I think it was Scott who brought this up in the previous half, is that sort of intuitively, if we can, ideally for these explicit construction problems, we can go from just a completely non-constructive proof all the way to an explicit construction. But for some of them, maybe an intermediate step, like we have in certain examples where we have explicit constructions, is that we just get a way to, we can just improve the non-constructive argument a little bit by making sort of the encoding step efficient. So if you remember, what I mean by that is that in the typical non-constructive proof, it implies some decoding algorithm which can decompress every sort of a compressed representation of every bad object. And if we can sort of improve this argument so that also the compression is efficient, then sort of that now reduces the explicit construction problem to this lossy code problem. And so an example where this might come from, I should have put this in the slides, but if we think about, like I said, a very prominent example of important explicit construction problems is to construct Boolean functions which are hard in some model of circuits. And if we have a learning algorithm, a non-trivial learning algorithm for a class of circuits, that will imply a compression algorithm, which is, this is like a generic connection, which is known. If I can learn efficiently a certain class of circuits, then given a truth table that's computed by one of these circuits, I will be able to efficiently compress it down to a smaller number of bits. And so if we ever get into a situation in the future where we get a learning algorithm for a class, but we don't quite have very strong explicit lower bounds, then we would be in a situation where we'd be interested in understanding this lossy code problem. So these motivations, I admit, are like a bit sort of backwards, bending over, trying to justify the problem. I think mainly the point is this is kind of an interesting derandomization problem in its own right, which shares many of the properties of the range avoidance problem, but we're going to be able to prove some cool things about it, which we can't prove for other derandomization problems. So
there's a question whether you want to say anything more about the connection to primes, if there's time about, or.
Yes, I can. So the situation here is that, so it's an open explicit construction problem, which is very cool that I didn't mention, is explicitly constructing a prime number. So you're given n, just the number of bits, and the goal is to produce like a n-bit prime number. Let's say it has to be bigger than 2 to the n or 2 to the n minus 1, which is a prime number. And this problem, it reduces to range avoidance. It's, for certain technical reasons, it falls in like an even easier class than range avoidance. But we don't know a polynomial time algorithm for this. We don't know a deterministic construction. And what you can show is that this is, I showed this in this paper here, and it's based on an argument in bounded arithmetic from Paris, Wilkie, Woods, that you can reduce this problem of constructing a prime number to this problem, this lossy code problem. The only unfortunate situation is that the circuits C and D require a factoring oracle. So, this is non-trivial because a factoring is not believed to be like NP complete. So it still puts it in a class that's sort of intermediate between a range avoidance and lossy code, but it doesn't reduce it to lossy code unless factoring is in polynomial time, which we don't think it is. So I put that there as like some connection because as is, that result is like kind of weird and not that strong. I strongly suspect that you could improve their argument and make it really a reduction all the way to the standard version of this problem with no factoring oracles. but I don't know the answer there. So that's why I said connection and not like a strong argument, because it has this caveat of you need to factor in. So anyways, so the interesting question for this problem is whether it's in polytime. So remember, for avoid, it was already interesting to see whether it's in P to the NP, but because lossy code is like a NP search problem, it's trivially in P to the NP, and really the question is whether it's in polynomial time. And if you recall, for range avoidance, we expect that it is in P to the NP because we were able to show that it's actually equivalent to a certain circuit lower bound, that specifically showing that e to the NP requires exponential circuit size. So sort of the motivating, so what I wanted to say about that is that this result, which I mentioned before, that avoid being in P to the NP is equivalent to a circuit lower bound, is in line with this broader range of what are called hardness randomness theorems, which show that assuming a certain circuit lower bound gives you actually an algorithm that de-randomizes some randomized problem. And so there's other examples of this, the most famous of them being that if we assume that a class E, this is exponential time, requires exponential size circuits, then we can actually show that BPP equals P. So this means we can de-randomize every decision problem, every algorithm that solves a decision problem in polynomial time randomly. We can remove completely the randomness from it. And under this same assumption, this also lets us de-randomize search problems like lossy code. So that would put lossy code in polynomial time. So we expect the answer to this is positive. And sort of the question I'm curious about is that, this lossy code problem, it seems like a much more structured problem than a general BPP type of problem. And so the question I'm going to address here is, like, can we de-randomize this under sort of weaker or just qualitatively different assumptions, hardness assumptions, than sort of the really high-powered assumption that lets us de-randomize BPP? So this is sort of the question that I'm going to answer here, or I'll give one answer to it. I think probably there's many different answers you could give. So what I'm going to show is this kind of bizarre result that we can de-randomize the lossy code problem. We can solve it deterministically if we assume a very different kind of lower bound assumption. And the lower bound assumption we're going to consider here are time-space trade-offs for a Turing machine. So I'll explain what all of this means. So what I mean by a time-space trade-off, just like if we scroll back in this hardness randomness, on the left side, we have some lower bound assumption that a certain problem is hard for algorithms to solve. So similarly here, we're going to have a lower bound assumption of a different form. Our assumption says that there is some fixed positive constant, epsilon, so that there are problems that are solvable in a certain amount of time, t of n, which cannot be simulated in the following way. We can reduce the space down to t of n to the epsilon while keeping the time only t of n to the 1 plus epsilon. So what I'm saying is there are problems that are solvable in a certain amount of time t, where the space cannot be significantly reduced without incurring like a super linear blow up in time. So I think I'm going to stay here for a second just for people to digest this assumption. Like one thing, so we strongly believe this to be true. In particular, if we think the relations that we conjecture to be true between time and space in general, like p space is not equal to x, and L is not equal to p, and these things, we believe that there are problems that are solvable in a certain amount of time and that the space can't be reduced significantly at all. So regardless of the time overhead. So, but our assumption here is like much weaker than that. We only need to assume that there's a problem solvable in a certain amount of time, so that maybe the space can be reduced in general, but in order to reduce the space, you need to incur a super linear blow up in time.
Is there a formal connection, or is it just intuitive? Because it's, I mean, sometimes I mean, for instance, P versus log space, then you would have to be much more drastic in your reduction of space, right? Here I'm still allowing you n to the epsilon potentially, which is a fair bit more.
Yeah. So sorry, the connection is just like we conjecture that, P is not equal to L. Probably we conjecture actually that P is not contained in space, n squared n.
No, so I agree that this is extremely believable.
But that's a great question. Yeah. So, okay. Something that's true also about this this theorem I'm going to prove is that it scales. I'm setting this parameter like t of n to the epsilon. If we instead had like polylog t of n, we would get still the same theorem, but the connection to the lossy code problem is that now the algorithm runs in more time. Now it would be sub-exponential. So it sort of scales with the parameter regime. But yes, in this case,
okay, I see.
Yes. So the point I want to make is that yes, it's a very believable assumption, but also that it's much weaker than these sort of assumptions like P is not equal to P space or things like this. We just need to assume that it's not possible to get a strong savings in space without incurring at least a little bit like superlinear blow up in time. And thinking now, I should have actually rearranged the slides a bit. I mentioned in a later slide that we do know trade-offs like this to hold when the time t of n is linear. I'll get to that later. So sorry. All I was going to say is that we know things that are somewhat close to this in a certain sense. But the specific assumption we need here is not known. And so I'm going to show that an assumption of this form is going to be able to let us de-randomize this lossy code problem. One more caveat I'm going to throw on this problem, lossy code, is that instead of thinking of this as a problem where you're given like an input, just somebody describes to you the circuits C and D, we're going to imagine that we have like instances of C and D of this lossy code problem that are defined like uniformly by a polynomial time algorithm for all n. And this is, if you think back to the range avoidance problem, this is sort of the natural situation that arises from explicit construction problems. Like for each of the explicit construction problems, like let's say constructing a Ramsey graph on n vertices, like for each n, there's just one instance of range avoidance that's defined for inputs of length n, which that problem reduces to. So so it's like sort of the interesting cases of solving range avoidance arise naturally actually from just this one sequence of instances, one for each input length, that are sort of uniformly defined. So that's what we're gonna focus on here. I'll explain what I mean by focus on this. So what we're going to show is that assuming, sorry, this is, I don't know why this is theorem 2. This is a theorem though, is that assuming a certain time space trade-off, which I'll state formally on the next slide, it's exactly like what we said before. We're going to be able to show that for every pair of polynomial time Turing machines, C and D, which define, I'm going to say that they define a compression scheme if C takes a Boolean string and decreases its length by 1, outputs something which is smaller, and D takes something of a certain length and expands it by 1 bit. So naturally, if I have a pair of Turing machines with this behavior, I can think of these as defining for every input length a compression scheme, where C is going to compress something down by a bit, and D is going to expand it back. And for every compression scheme like this, I can say, define the following sort of explicit construction problem of, given n, I want you to produce an n-bit string which fails to be compressed by this scheme. So, sorry, I know this is like kind of a lot to absorb. I'm defining I have one pair of polynomial time Turing machines that define what I'm calling a compression scheme. And what we're trying to do is solve the explicit construction problem for this compression scheme, which is I want to be able to, in polynomial and n time, produce one example of an incompressible string of length n. Please ask me to pause or ask any clarifying questions if you need. So what we're going to show is that for every possible pair polynomial time compression scheme, we have a polynomial deterministic algorithm for this problem, assuming a certain time space trade-off assumption. So in particular, just restating this, we're going to show, restating this in a way that's a little more consistent with our proof. We're going to show that one of the following is true. Either for every, like I said at the top, for every pair compression scheme, there's an efficient deterministic algorithm that can produce an incompressible string. Or if this fails, then we're going to show that for sufficiently large enough time bounds T of n, every T of n time computation can be simulated in T of n to the 1 plus epsilon time and T to the epsilon space on a one-tape Turing machine. And we're going to be able to do this for arbitrarily small epsilon. So a little caveat, which I want to say, don't focus on this for now, is that we're only going to get the simulation for large time bounds that are like at least exponential in input length. I would say don't worry about that for now. The point is, what we're going to show is, so our time space trade-off assumption is that 2 is impossible, that there's some computation which we cannot shorten the space too much without increasing the time. And this theorem, saying one of these is true, is going to imply that if we assume that time space trade-off assumption, we get this deterministic algorithm for lossy code. Cool. So the idea that I like to think about this proof is like kind of by how would I say this? Yeah, so we're gonna prove essentially by contrapositive that we're gonna assume that 1 is false. So 1 says that every pair of compression schemes I can always find incompressible strings. We're gonna assume that there's some compression scheme, polynomial time computable, that I can't find. No efficient deterministic algorithm is able to find an example where it fails to be a good compression scheme. And I'm going to say that this is we're going to think of C and D as being a counterexample to the pigeonhole principle that says that every compression scheme that uses fewer bits is lossless. So to a polynomial time observer, none of them are able to find the example where this scheme fails to compress a string. And so we're going to think sort of intuitively in this way, it's not actually true, that this is like a counterexample to this pigeonhole principle, and that C and D are actually a valid lossless compression scheme that can compress every n-bit string using fewer bits. And what we're going to show under that assumption is that we're going to use that compression scheme to efficiently simulate every time t computation using much less space and only a small overhead in time. And intuitively, the idea is that if we have this way of compressing information losslessly, then we're going to be able to use it to compress the memory of a computation. But we need to do it in an appropriate way where everything actually works. Like when I defined this compression schemes, I said that they compress just by 1 bit. I'm going to make a simplifying assumption, which is without loss of generality, that they actually compress like 2n bits down to n bits. So C takes 2n bits, compresses it to n, and then D recovers n back to 2n. And our running assumption is that to any polynomial time observer who's searching for a counterexample, who's searching for an incompressible string will never find one. And so to a polynomial time observer, it looks like C and D are actually a lossless compression scheme.
So one thing that I might be missing, but maybe I can point out that C and D don't compress correctly, except very rarely. There are certain input lengths that are really, really hard for me.
Yeah.
Like Mersenne prime lengths or something, but for all other ends I can deal with.
Yeah, so we need to specify specifically, so there's going to be a correspondence with basically for each input length which the time space trade-off holds, you will be able to solve on that input length or on a related input length the compression problem, or vice versa. So let me, to simplify things, let's say we're going to assume now that the compression, that it's hard to find examples for all input lengths, and then we're going to get a simulation, a low space simulation that works for all input lengths. If we only instead assume that there were infinitely many hard input lengths, then we would get a simulation, a low space simulation that works for infinitely many input lengths. So it's kind of scales with whichever way you want to assume it. Does that make sense?
It does make sense. I don't immediately see, because it seems like you need a contiguous interval to go from 2n to n, but I'm happy to trust you on this. And also, let's just assume that it's hard for all n for now. I still don't see how to do it. So it's really interesting to.
Okay, cool. Yeah. So yeah, let me specify. When I said let C and D be a counterexample, let's say for every polynomial time algorithm that's like searching for an incompressible string, it won't be able to find one on more than finitely many inputs. So that's going to be our assumption. And we're going to show under that assumption, we can use C and D to simulate any algorithm using much less space and only a small overhead in time. So how are we going to do this? Well, we're going to start by just fixing some epsilon, which we're going to claim you can take to be arbitrarily small. And we're going to let M be any Turing machine that runs in some time t of whatever its input length is, that we're just going to abstract away what the input length is and just imagine we're trying to simulate a machine that runs in time t. And the idea is, so for starters, we're going to set some parameter w to be whatever t is to the power epsilon, so quite a bit smaller than t. And we're going to focus on our compression scheme and how it behaves specifically on strings of length w. So, so the compressor can take two w-bit strings and compress them down to 1, and the decompressor can take 1 and decompress them to 2. And great. And so the idea is, like I said, what we want to do is somehow use this compression and decompression scheme to sort of compress down the memory of our computation. So how are we going to do this? So the idea is we're going to take, imagine drawing this tree diagram where we have our function d. Remember, it takes in w bits and it spits out 2 blocks of w bits. And we're going to imagine, like, what happens if I compose this function sort of k times into this perfect binary tree. I haven't told you what k is yet. Just think of it as some parameter I have yet to set. And so if I do this, right, if I imagine I feed some w-bit string in the bottom and I sort of let it percolate down to up to the leaves of this tree, it's going to output 2 to the k w-bit strings. I haven't told you what the point of this is. Just does it make sense to everyone just that this is a picture I can draw, that I'm just repeatedly composing this function with itself?
So somehow, I'm sorry, like you're somehow going to simulate what the low space machine on this extremely compressed thing in some somewhat efficient way?
Yeah, so I'll explain in a moment. The idea is
way.
originally we just have a machine, an arbitrary machine that runs in t time steps. Like we can think of it as a random access machine. That's the model we'll be able to simulate. And we're going to sort of somehow use this tree to simulate its computation in an extremely space efficient way. So I'll explain right now. So if we have a machine, let's say on a random access model of computation that runs in t steps, then we can always assume that if the space it uses is at most t. So it uses some t memory cells, and we're going to assume it's random access. So at each step of computation, it can like access unit time a memory cell and change its contents based on some instruction that it has. And so the idea is we're going to sort of initialize this tree. So we're not actually going to write down the whole tree in memory, but we're going to imagine hypothetically for now in our heads that we have this tree, which, let me just put a reminder here that w is t to the epsilon, where epsilon was some small constant. And we're going to have this tree be of depth log of t, so that the number of leaves at the top is exactly t. And what we're going to ultimately do is think of the leaves of this tree as sort of a simulated t-bit memory. And we're going to be able to store this memory in a compressed way by only storing a certain value at the bottom. And the contents of the memory are going to be described by what I get if I feed this bottom input through the entire tree. And sort of the thing that we need to prove is sort of that this simulation of this memory in this weird way is going to work unless I can find an incompressible string for the compression scheme. So let me explain it a little more. So if I plug in some seed, I'm calling it a seed, some string y. Remember, this is 0, 1 to the t to the epsilon. If I plug in some input y at the bottom and I feed it through this tree, then at every leaf I get some string. And so I'm going to imagine this small seed, what I'm calling a seed y, is only t to the epsilon bits, but it's going to represent about t bits of memory at the leaves. In the sense, I'm going to think of it, this cell of memory contains whatever value I get when I feed y through the functions and reach that leaf. And if you remember, at the leaf, each of these are like w bits long, but I'm just going to treat them as one bit of memory in this, just for simplicity. So I'm always going to imagine that I store a value there that's just a bunch of zeros, w zeros in a row, or w ones in a row. And so this is the basic idea of our computation. We're going to say that we're going to show somehow that we can maintain this t bits of virtual memory by, in reality, only storing these t to the epsilon bits of this seed. And in order to make this work, we need to, like, the following like virtual memory operations, where the first one is we need to be able to sort of initialize all the leaves of the virtual memory to 0. We need to, at any step in this simulation, be able to access a certain cell of the memory. And then sort of the most difficult is we need to be able to update a certain cell to a new value. And what we're going to show is that, like, we can sort of, in this weird virtual simulated memory, we're going to be able to perform all of these operations in such a way that if an operation ever fails, then I find a witness to the pigeonhole principle. I find some incompressible string for my compression scheme. And yeah, so so here's the idea. So the first operation I wanted was some initialization step, which set all the leaves to 0. How am I going to do this now? So if you remember, this picture I drew only involves D, but I also have this compression scheme, this compressor C, which can essentially invert D. So what I'm going to start with is I'm going to plug in 2 blocks of 0 to the W, just all 0 strings, into the compression. And I get out of that some string x1. And then I'm going to plug in 2 copies of x1, again, to get x2. And I'm going to repeat this the number of times the depth of my tree. And if at each point I plug in something to the compressor that the decompressor will then return to me, then at the end of this process, I get this value, x whatever, at the bottom, which when I feed it through should give me all zeros at the top, right? Because the point is, if I first compress these 2 zeros down to x1, I can check if I found a counterexample to the compression scheme. If not, then x1 should spit out these 2. And then, you know, I got x2, so x2 should spit out 2 copies of x1, and so on down this tree. But the point is that I was able to sort of, in a simulated way, initialize all of the leaves simultaneously to 0, but the actual computation time I spent was only proportional to the depth of this whole construction. So it was only log t times, you know, I have to evaluate the functions c and d, which I assume are computable in polynomial time. So in particular, in time t to the, you know, polynomial in t to the epsilon.
So, sorry, could you say I could fail in this step? We could fail, in which case we have a collision, or this step never fails?
Wait, say it again.
So can we fail in this step? And
yeah, so we can fail in this step. So for example, I skimmed over this kind of fast, but in the first step, I have 2. I plug them into C and get x1. Now what I'm going to do is, using D, that E of x equals W comma 0 to the W. I check if this is true. If it equals, then I found some string, in particular the string is 0 to the W, 0 to the W, compress under this scheme.
I see, and the reason for doing this is that you will actually use, well, if the compression isn't correct, then whatever might happen later with your simulation. So you want to check these things.
So they have to check. We can imagine, like, I'm blindly, and then if one of them failed during this, another algorithm could go through and check, and it would be able to find an incompressible string. So it doesn't actually matter in doing the checks at each step, but the point is just that we're going to show all of these steps. If at any point one of these steps have a property that would make it work, then another deterministic algorithm try the same simulation and check it.
Okay.
And
yes. True. Okay. Yes. If I mean, you could try to discover collisions online, or it could be part of a post-mortem analysis, is what you're saying.
Yeah, exactly. So either. So yeah, the point is that the number of operations I needed to do only scale with the depth tree, which is log t, and then I evaluate c and d, which are assumed to run in real time in the input length, which is t to the epsilon. So in other words, it's t to the epsilon time overall. The second operation I need is to read bits of the memory. A very simple one. The idea is, given some index of a leaf, I just start with whatever seed is, my virtual memory seed. I feed it through this function d, and at each point I only save the half of the output that follows like the path that I want to get to the leaf. And then the time complexity here again is just proportional to the log times the t to the epsilon, which is evaluating the function d a bunch of times. So this step doesn't actually, I don't even need to use C. And the final step we need is this update. So I imagine at one step I have stored at the leaves some values of memory that I'm using in my computation. And what I want to do is be able to set a bit of this virtual memory to a new value. What I want is to be able to, that I can perform some update on my seed Y, which sort of virtually simulates updating a particular cell of the simulated memory, of the virtual memory. So here's the idea of how we do this. So I say Y is my initial memory state, like it describes my initial memory state. And sorry, I just clicked out of it. Can everyone see my screen again?
I think it's slowly coming back.
Screen?
No, you're back. Yes.
Okay. So I have this initial Y, which is like representing my virtual memory. And I have this of a certain leaf that I want to get. So what I'm going to do is first I'm going to follow just this access step where I follow the tree and get to whatever currently stored here. But every time I sort of branch, I'm going to keep track of the other value, right? So when I first feed, I get half of the value that I'm actually, and then I also get some other half before I was ignoring. And now I'm going to perform the following process, is that say I wanted to replace this value X with the new, which I'm calling S. Well, what I want to do is with a new sort of value that would occur, so that if I feed it through, on the one hand, I get the updated value I want at the new cell. On the other hand, if some memory on this path, they should see. So I should change the memory cell I wanted to change. We're going to take this new value together with the off branch old value, and we're going to try to compress them. New value I'm calling here V. And like we could either think in an online fashion, maybe I check, see, did that compression actually? If it did, then fed back through D, I know get back S. So I'd be happy. So now what I want to keep doing this in a way that for F that doesn't go to the changed memories, I'm going to maintain what I had before. So I'm going to now, I have this V1, and then I also branch over here, and I don't want to change cells on that branch at all. So let's take V1 together with this old value, whatever was here, and I feed them again through my compression. And I just keep doing this at each step. Finally, when I finish this, I reach a new value of my seed. And you can show, like, the argument we just kind of went through is that if at each step I never witness a problem with my compression scheme, then I'm able to update my memory in a way that the access operation, if I apply it to this one memory cell I wanted to change, I'll get the new value. But if I follow any other path and look at a different memory cell, I'm going to preserve whatever was there before, because I always preserve these off-branch values.
And the time complexity of it, I mean, C and D are fairly fast compared to the overall running time of your algorithm, are they? Or
yeah, so the point was C and D are polynomial in their input lengths, which we set here. We're running them on inputs of length t to the epsilon.
Oh, right.
So C and D will run in time t to the O of epsilon. And the point of all these operations is that these operations run in time bounded by log of t, which is the depth of the whole thing, times whatever the t to the O of epsilon term is from evaluating C and D. So the overall runtime of each operation of a update, access, or an initialization is each t to the O of epsilon. And so, yeah, I'll get to this. Before I get to that, the high level thing, did this step make sense to people, or did people have questions about it? So the high level thing is that I've defined each of these sort of virtual memory operations in a way that takes t to the O of epsilon time. And to simulate a t-time computation, I just need to do t of these in a row. And the only internal memory state I need to save between steps is the seed, which has length the epsilon. Plus maybe a constant number of like pointers or basic to, storing the instructions of the computation. So if I want to simulate
you're picking up a log t somewhere also, but that is small compared to t to the epsilon, I guess.
Yeah, exactly. I'm absorbing that into the t to the O of epsilon term, but there
okay,
is the
fine.
log. Yeah.
So, but the point you're saying, this is actually like fairly, the overhead is only, like, you probably said this already, but the overhead is only t to the epsilon. So this is actually pretty fast also in the grand scheme of things. Not only is it amazingly space efficient, but it's like...
Yes, that's exactly the point, is that the time overhead per step is only t to the epsilon. So in other words, I just said it here, that the space is t to the O of epsilon, time complexity is just this multiplicative overhead of t to the epsilon. In other words, the overall time is t to the 1 plus O of epsilon. Yes, and this is the interesting thing about this simulation is it's both also very time efficient. Because we're doing these interesting games with this tree, we're able to get this time efficient. And to the point, what that constant in the is, I can bring it to 0 by taking epsilon suitably small, right? So to rephrase this, I can get a simulation in time t to the 1 plus epsilon and space t to the epsilon. And this weird assumption that a compression scheme that no determinant find counterexamples where it fails. That this simulation would always have to work. Contrapositive is that if I assume this computational lower bound of a time-space trade-off, that means that there's some mentally this simulation has to fail that computation. And if we think like going through and give us a sequence of operations which would form a counterexample where the compression scheme. And so, yeah, essentially the idea of the. Sorry if I had to kind of rush through it or questions. I'm totally happy to clarify anything. But that's the idea.
And the size of the counterexample again is like, or is it? I mean, I'm worrying that this is fairly, or maybe I shouldn't worry about the. I mean, or I mean, we're fine with any counterexample to lossless.
Yeah. So the parameters are set up in a kind of, it's kind of a weird way where I said, so yeah, if we assume a time-space trade-off that holds, let's say, for all sufficiently large input lengths, you can't simulate the algorithm in this non-trivial way, then what I could do, I described it as I have the time t, and I set the input length I'm going to solve lossy code on to be t to the epsilon. If I think of it in reverse, I want to solve lossy code on input size n. Now I'm going to run the computation, the sort of the hard computation in time n to the 1 over epsilon. So now I'm trying to simulate something that takes much more time. Is the sort of reverse way to look at it. Does that make sense?
Kind of, yes. Yes, a little. I like yes, kind of, yes.
I can say more. So, what was I going to say? Okay, yeah, the one thing I wanted to mention is that, so an extra note of this proof is that we're able to simulate a random access machine that runs t, and the simulation, it's very easy to show, can actually run on like a one tape turn machine. And it sort of the reason I mention this is that when the time bound is linear in the input length, we actually know a lower bound that's a time space trade-off for this problem, and it actually applies to the very simple problem of recognizing a palindrome. The issue is that for this proof to actually like go through, I didn't really explain this in detail, but I kind of swept it under the rug to some extent, is that we need t of n to be exponential in the input lengths. The reason is that we need to assume that the computation, that there's some hard computation that I can't simulate with less memory. But if let's say the computation runs in time, linear in the input length, then all that the lower bound assumption just tells us that there's some input of length n on which the computation fails, and it's still, the problem would be now to find what input that is. Versus if the computation is running in time exponential in the input length, then just assuming that there's a lower bound is the same as assuming that I can efficiently find the input where it fails, because there's only, in terms of runtime, only logarithm inputs. This is
are you saying sort of that I have to pad somehow the input length so that I have time to search exhaustively for a bad input somehow, or you
exactly
saying something different?
So exactly what I'm saying. Or you can say we need the lower bound to hold for us. So for a sort of unary problem, like a problem with unary input, or so that the time-space trade-off holds, if that makes sense. So it's really the difference between the time-space trade-offs that are known, and the sort of the input length, the same order as the runtime of the algorithm, versus if we prove that to parameter time-space trade-offs, but when the input is much smaller than the runtime, then we would suddenly be able to get these derandom. And so in time, I am already over a bit. So I was going to make like the proof that range of construction is complete for this class, which has a similar proof. Also, I'm happy to stop.
I mean, it's really, I think it's up to you how long you want to entertain us. I think everybody is like free to leave whenever they want. So.
Okay, all right. I guess I'll explain this last thing, but if anyone leaves, I won't be insulted. It should only take another 5 minutes, I think. So that kind of concludes what I was going to show about this lossy code problem. And now I just wanted to return really quickly to the original range avoidance problem and prove this result I mentioned in the first part of the talk, that we can reduce range avoidance to the construction of a hard truth table. And the reason I say this to the end is that the proof technique is going to be very similar to what we just saw. It's not going to really involve anything new. It's going to be actually much simpler. So like before, we're going to start with some instance of range avoidance. And what we want to do is like reduce it in P to the NP to the problem of constructing a hard truth table. The first step is that so in general range avoidance, we just have the number of outputs is one more than the number of inputs. There's a very simple reduction to the case where the number of outputs is twice as many. So just as before, we're going to focus on this case, and it's without loss of generality. And so the idea is we're going to draw the same exact picture. We have this function that stretches n bits to 2n bits, and we're going to sort of into this tree of depth k, where I'm not specifying yet what k is. And so for any k, I can imagine writing down this tree, which like iterates d function. And if I sort of just put output behavior of this tree, I can think of it another instance of the range of, which now, before it took n bits to 2n bits, now it's going to take n bits to 2 to the n bits. Does this make sense? So like I can just, here I feed in n bits, I feed it through the k times n bits at the very top. And so I can just think of this as another instance of the range of, and I'm calling that d star. I guess there should be like k also. So yeah, I just said that. I instance of range avoidance, get this new instance d. We're just going to make two like observations about this, is that the solution to range avoidance for this d star, I take one for the original d, time that's polynomial in n 2 to the k, where k was. I can do that with an NP oracle. I'm going to need the NP. So this proof is very similar to like what we saw in the just now in the low space simulation thing. Say I had some string which is outside the range of what I'm calling, and I imagine right all the bits of whatever that's top in sequence. I'm just going to go through this entire tree and like I first look at these bits here, and I use an NP oracle. Before I was using this compressor C, which I'm just going to have an NP oracle. Use the NP oracle to find if there exists some string which maps to these. If the answer is no, then right? I just found something in the range of D. I solved range avoidance for D and I'm done. Otherwise, I am able to compress these down to some string here. I'm going to do that the same for here, compress it to here, 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 blah, blah, blah. And I continue all. And if I never find a solution to range avoidance for the little d, then I'm able to compress this whole y down to some input over here. Assume that y is a solution for range avoidance on the map d star. That has to be impossible. So there must be some point at which you find a solution. And the running time of this is just proportional to the number of nodes in this whole tree, which is why I said it's proportional to 2 to the k. So does that make sense? So given any star, I can find with an NP oracle. And then the second claim is that any 2 to the k, any string outside the range of, any string in the range of d star, if I view it as a truth table, it has a circuit complexity. Why? And specifically has circuit complexity, whatever the size of d is times k, with the depth of my construction. And this is very similar to, again, the proof with the low space memory. It's just if I imagine I have in the range of this function, writing it down and thinking of it as like the truth table of some. Well, if I want to compute a certain index of this, all I have to do is like to store x, whatever the preimage of this under this, and then to compute this index, I only do d times k is only proportional to the depth, because I just follow the ways before and what's at that particular index. If I think of this as like a circuit which is describing that truth table, its size only scales d times the depth of the construction, d times k. And so if I combine these and I set the parameter to be a suitable, so I have some fixed epsilon, parameter k to be this logarithmic e times something 1 over epsilon, then I'll have 2 properties. The first is that the running time of by having a solution for d star k, that's going to be polynomial in, I don't see here, this should be d. That's the original instance to range avoidance. I set k to be logarithmic in the size of the instance. But on the other hand, I said that everything in the range of d star has circuit complexity k times d, which is at most, based on what I set k to, this is going to be at most the output length of d star raised to the epsilon. So in other words, any 2 to the k times n bits truth table whose hardness is at least its length raised to the power epsilon must be outside the range of this function d star. So if I'm able to produce these high complexity truth tables, then necessarily they solve this d star instance of range avoidance. And then by this other claim, where was it here? If I have any solution to this d star instance, I can use it to find a solution to the original d. But I need to use that NP oracle. So that's the idea of that proof. And that's all I wanted to say.
So about this, yeah. No, that's fine. So this NP oracle, I was the d star thingy, I'm missing something. So yeah. You're using an NP oracle to find what? The strings that map to your string?
So yes, exactly. So to find pre-images under D, to invert the function D. So we have the step that we use it in is this step where we wanted to say that any solution to D star, it could be mapped back to a solution for D. And the idea is we write down a candidate solution for D star.
And a solution here would be something that is outside of the range?
Exactly. So something y that's
okay, let me tell you right where I lost you. So okay, then you can help me get back on track again. So this is going to be an NP algorithm. So obviously sometimes I'm going to make bad guesses, right? So and I sort of, how do I distinguish between whether I made just a bad guess of the pre-image or whether there truly was nothing there? Am I making sense at all?
Oh, okay, yeah. So let me clarify. When I say an NP, so this is what we call a P to the NP algorithm. So this is like a polynomial time where I can make queries to a SAT oracle. And so it's not the same as a non-deterministic algorithm. Like I don't make incorrect guesses. I can determine in unit time whether a certain string is in the range. And then I can use binary search to actually find a witness to this, again, in polynomial time.
Ah, okay, that's probably where, okay, good, great. Mm-hmm.
Yeah, so that's a great, so yes, with P, NP, I can, not only I can solve, I can determine yes, no for any NP problem, I can also actually find always a witness deterministically by using binary search.
Okay, got it. Mm-hmm.
So using that NP oracle, I can, for each, I split this up into like these blocks. I use the oracle to try to find a preimage for Y. And I for sure either determine that Y is outside the range and it's a solution and I'm done. Or I actually find a specific preimage value. I do the same thing here. I find a preimage for that and for this. And up until the point where I solve range avoidance for D, I keep sort of inverting this whole tree down to lower levels of the tree, which are going to output the things above.
And I know for sure whether I am successful, and I can't be successful all the way is what you're saying. So
exactly. So I know for sure if I'm successful because I have this NP oracle. And if I was successful all the way and I got to here, that would be a witness that Y is in the range of D star. But my assumption is that I have Y that's not.
Yeah. Mm-hmm. Mm-hmm. Yes, got it. Thank you. Thank you so much. Mm-hmm.
Absolutely. So, yeah, I think the end of what I wanted to cover. And just going to your question, Jakob, a while ago of this pseudo-deterministic NP oracle algorithm that I mentioned was a new result that was discovered. Also, so I wasn't able to describe, simply everything that goes here, but it uses also like these sort of analysis with these trees, creating the function a bunch of times, doing some sort of analysis on what this tree looks like. So that's a vague explanation of what's going on in that. It involves more. But yeah, that's the extent of what I wanted to cover in this. People got something out of this. And very much.
Thank you so much. I mean, this is amazing. Thank you. Again, I'm clapping on behalf of the audience. Yeah. And any questions from?
Yes.
Yeah.
So when I draw the tree, what jumps to my mind immediately is this pseudo-random generator.
Yeah, totally. So I would have mentioned this connection with more time, or I was debating what to mention or not. But so there's two places this tree kind of originates from right around the same time. One is GGM, the pseudo-random function generator by GGM. And the second one is in Paris, Wilkie, and Woods, where it's a paper that I guess in modern proof complexity terminology was the first paper that gives a proof of the weak pigeonhole principle in bounded depth Frege. And they use also basically identical construction. And both those papers came out like the same year, I think, or something. It's kind of funny, totally different areas. So yes, it's very influenced by both of those. Formally, there is some form of connection more to the bounded arithmetic side of things than GGM. It's the same construction as GGM, but sort of the analysis we do on it is know more. I've thought at various points, are there formal connections between arguments involving generators which are of the same form as range avoidance instances and range avoidance? And there's a lot of connections between the techniques that work for both of them, but not actual formal connections, as far as I know, that say, we can transfer results from one problem to another. Yeah.
Okay, thank you. I think my question is much simpler. I mean,
sorry.
in order to...
I jumped ahead.
There are other kinds of pseudo-random function generator which stretch length. Stretch the output length. Would you think that they would, in other instance of this pseudo-random generator besides GGM, would give you trade-off results, for example?
So that's a good question. So I know in terms of actually building a pseudo-random from a PRG, construction which has like, in my mind, the parameter to change perhaps is like the depth of this construction, the layers of the tree there are, because for range avoidance, this would be important without going into too many. And it's like a big open problem in cryptography to improve GGM in essentially any respect. There's an improvement called Levin's trick, which doesn't seem to have to the range avoidance problem. And other than that, as far as it's kind of an open problem to give significant improvements in terms of depth or other parameters of the GGM construction of a PRF from a PRG. So as far as I know, very curious if there are, but when I have looked through this, understanding it's what else can be done. There are constructions of PRF from other types of cryptographic assumptions, but the one that's just from a PRG PRF, this is, from my understanding, it essentially the best known, or the only major known one. Yeah.
The one question that is so vague that I don't even know whether it makes sense is like, I'm thinking, if I don't want to analyze Turing machines because they're so complicated, but I'm interested in other computational models, like I don't know, Grosvenor basis computations or whatever.
Yeah.
Is it conceivable that I could somehow scale down these results to hold in other computational models, and where in these computational models I might even have, like, because again, if you go to things like, resolution / sat solving or Grosvenor basis computation / polynomial calculus, you actually do have some time space trade-offs.
Yeah, that's a great question. It would be hard for me to imagine sort of this exact proof to some really of computation like that. But I think a more general question is like, can we, I don't know, give strong instructions that show that this class of explicit reduces to some lower bound from, like, I don't know, some model of computation? I think that's a really interesting question, and really hard to imagine there are more reductions. For this specific time space, it would be hard for me to, I don't know the model that you have in mind, but for example, like, I don't know, any model that's a lot weaker than Turing machines, it would be clear to me how to adapt this.
Yeah, I mean, usually what breaks is like this kind of mathematical reasoning that you have along the way is like, I mean, suddenly if you may, for instance, like one problem you have in proof complexity is that we can entertain ourselves with proving lower bounds for lots of different NP-complete problems, right? And the reason why this makes sense is that, well, typically our proof systems are too weak to understand NP reductions. So like asking whether clique is hard and whether coloring is hard, these are two very, very different problems, because like resolution totally cannot compute any reduction in between them, right?
Yeah.
So that might be something that the question is like how sophisticated these arguments are.
Like, the arguments.
Which is sort of going in the direction of, I guess, but then, it's more, you go into the direction of, I guess, bounded arithmetic, where you're trying to do your proofs with one arm tied behind your back and see how it goes.
Yeah.
So
yeah, I mean, you could ask for this question. Yeah, like whether this is formalizable in arithmetic or something. And I mean, I'm not going to go down that road, but it would be an interesting proof complexity, like some of a time-space trade-off as a tautology, like let's say the one for palindromes. Could you show that this is equivalent to the weak pigeonhole principle using this type of argument? I think it could, over some system, some fragment of bounded depth Frege, I imagine you could make a sort of argument like that work, but I don't know.
Okay, any other questions or comments? Protests? Or should we just thank Oliver again for the this was fabulous. Thank you so much.
Absolutely. Thank you for having me. Yeah.
So thanks a lot, Rini.
All right. Sounds good.